Hi, I'm Lucas, and you're listening to Gradient Descent. We started this program because we're super passionate about making machine learning work in the real world by any means necessary. And one of the things that we discovered in the process of building machine learning tools is that our users and our customers, they have a lot of information in their heads that's not publicly available. And a lot of people that we talk to ask us what other people are talking about and what other people are doing, what are the best practices. And so we wanted to make all the interesting conversations that we're having and all the interesting things that we're learning available for everyone out there. So I hope you enjoy this. Brandon Rohrer is a mechanical engineer turned machine learning engineer / data scientist. He's worked on some incredible robotics projects and then worked on data science projects at Facebook and Microsoft. And currently he's a principal data scientist at iRobot. At the same time, he's an instructor at End-to-End Learning, where he's made some amazing videos on convolutional neural nets and other things. I'm super excited to talk to him. Brandon, it's really nice to talk to you, and thanks for taking the time. You've worked as it sounds like you've worked on machine learning at quite a range of different companies, and most recently iRobot. And so I can't help myself, but I'd love to just hear about what kinds of challenges you have at iRobot and robotics in general.
Yeah, thanks for having me on, Lucas and Lavanya. I really appreciate it. At iRobot, we get to actually support these little giant thick frisbees that run around on people's floors and suck up dirt. Those are the vacuum cleaners, and also there are mops, which are run around on people's hard floors and clean up messes. What's really fun about this is if you think about production machine learning systems having to deal with whatever input or badly formed requests that you might encounter. Imagine taking that to the physical world and you have something that is bopping around literally every type of home in the world. There's 30 million of these things out there now. And as hard as we try to imagine, we can't imagine all of the challenges that they will come up against. And so this is really fun from an algorithm design standpoint and just an engineering standpoint, making something that can get beat on, can have cats ride on it, can run into all kinds of things, encounter cords, encounter socks, encounter Legos, encounter Skittles. And how is it going to handle all of these things? That to me is really fun. It's the polar opposite of the sandbox, carefully prescribed problem where you know exactly what your data is beforehand and it's been cleaned up, so it's going to give you a good high quality answer on the other end.
I'm curious, I feel like I've had a lot of friends in the last couple of years kind of move from consumer internet ML applications to robotics. Was there big things? Was it a big adjustment for you? Were there big changes, or was it mostly kind of the same set of issues?
Let's see, definitely changes, but for me, this was coming home. So robots for me is where I started.
Right.
My degrees are in mechanical engineering, and my graduate work was all about using robots to rehabilitate stroke patients. So, knowing things that could break all the time and not to trust your sensors, that's kind of what I grew up with. Then when data science became a more common career path, I rebranded myself as a data scientist and went to agriculture, went to Microsoft doing cloud machine learning solutions for a variety of different companies. I went to Facebook infrastructure, which is a fascinating set of problems around keeping one of the biggest networks and set of data centers in the world up and going and running efficiently. All of these things, what I enjoy about them is that you could not ignore where the data came from. You had to know something about either the people, what state they were in when they generated it. You had to know about what pre-processing it had. You had to know about the assumptions that were made along the way. If you didn't know this, then you couldn't build good models to get answers out of it. And so robots just take this and they put it front and center and take it to the extreme, because if you don't know what a given sensor value means in the physical world, then it's really hard to build a good model around it and know how to interpret it. Naive models where you just throw things in, unless you get really lucky, they just don't work well.
So does that lead you to kind of like simpler models? Like, does it like, are you more afraid of complexity then for these applications?
So my personal strategy when faced with something like that is, if I don't know everything it's going to come up against, the biggest thing I want to make sure is that when it performs poorly, it doesn't do horrendously bad. So I don't know if you.
Well, so how do you do that? Tell me about that.
Simplicity is a good one. So knowing exactly what happens. One example of this is in agriculture. One of the hard modeling problems is I have a field, I have some corn seed, I planted on a certain day, I use this much fertilizer, here's what the weather and the precipitation is all season. How much am I going to harvest at the end of the year? If you had a model that could spit that out, you would have solved agriculture, or at least the yield problem in agriculture. But there are so many variables, and the model we were working with was a popular academic model that had literally hundreds of variables in it. And there's no way that you have enough data to train that model well. And what was really funny is when we did some analyses on that, using popular settings for that model, you could have a really naive model, which just estimated a flat rate for all fields everywhere for all conditions. And then this really elaborate several hundred parameter model. And the flat rate model did like twice as good.
Wow.
So
it's funny because I would think with like plants, there'd be like a lot of complicated interactions but I guess you just don't have enough data to know.
And you're exactly right. And that's why the many parameter model didn't do so well. It did account for a lot of interactions, but to get them to work the way they were supposed to, you had to get all those parameter values correct or in the neighborhood. And we just didn't have enough information to do that. So an alternative approach then is to start with a very dumb estimate and then incrementally make it a little smarter. I think by the time I was done, I was working with like a 3-parameter model and one for, precipitation and one for soil texture and one for something else. And to be able to check it each time and really just listen to your data. So same holds true then for robots or for anything else. It's like simple's good.
Simple's good. Is there anything else though, like to make sure that your models are sort of robust in the face of different types of data? It sounds like you're also maybe like kind of pulling apart the problem into sub-problems.
Definitely that. Some problems are amenable to that, and to the extent you can separate it into a sub-problem, then that is a great strategy.
Although not everyone thinks that, right? I mean, like sometimes people talk about sort of like end-to-end autonomy, right? So I do think that's a little bit of a point of view.
That's true. That's a good footnote. I will say that is my opinion. That pulling it apart is.
Sure.
I don't think that's generally accepted. I agree with you on that. But it is easy to get over ambitious about, to fall in love with your model and say, well, it explains potentially so many phenomena. Like it must be right if we can just get the data to train it correctly. But then when you actually in experience, like we've seen this even with some vision models, the actual high quality labeled data to train it well would cost so much to gather that it's impractical. And so in that case, the model doesn't do much. And if you close your eyes to that and move ahead with poorly labeled data, then badness happens and you get models that are worse than no model at all.
Yeah, I think we've all experienced that. I'm kind of curious. It's funny, I have developed a real interest later in life in sort of mechanical engineering and electrical engineering, and I feel like you've kind of gone in the opposite direction. I guess like one similarity that I've found, of sort of like mechanical problems and machine learning is that you don't get good error messages in either domain. But I'm kind of curious, do you think that your like background in mechanical engineering has like helped you in certain ways in machine learning, or how did you go about learning a new field? Because lots of people want to do it. And how did you like bring the knowledge you had to help you there?
in my case, it was motivated by a problem I was trying to solve.
Oh, cool.
And so in my work, we used robots to help rehabilitate stroke patients. We saw changes in their movements. A good research question is then, well, what's going on in the brain to make their movements get smoother? Like, what's going on there? And the more you dig into human movement, a whole collection of questions bubbles up. How does the brain control this hardware that's sloppy and that changes over time and that's not very accurate compared to, like, precision machine tool robots, and with huge time delays that would take any like off the shelf robot and drive it unstable. But the brain does it casually. Like, we do it like we're half freezing and our neuromuscular dynamics all changes. The brain compensates. We're drunk and all of the time delays change. Brain compensates. Like, how does this happen? So this was the problem that I wanted to solve, is how could I make something that could control a piece of hardware that I didn't know or understand very well, and it was going to change all over the place. And so that led me on the path of learning what I could about how the brain works, which, if you, from the point of view of, now I want to turn it into an algorithm, there are still huge gaps there. Even though we call neural networks, they have no resemblance at all to anything that goes on in the brain. So studying that and then figuring out, well, if it was successful, what would I want it to do? And that did lead me then into studying different signal processing methods and different algorithms, different families of algorithms. And then once I started being a data scientist for my day job, then aside from this research interest, there was a whole other, like, professional motivation to dig into these things. And then once I started writing tutorials and teaching these, then there become even more motivation to learn these things and to be able to understand them well. So it kind of built on itself. That original problem of kind of building a general purpose, brain or controller that you could pop into any robot and then it could learn what to do with it, is still a long-term passion of mine. It's my, like, personal 30-year project.
What makes that hard?
The real world, the robot's never going to experience the same thing twice. You're never going to get exactly the same camera image 2 times in a row. So one thing that's hard is you have to deal with always new experiences. So you can never learn exactly what to do in this situation. So you have to learn what other situations are similar. That sameness is very hard. And we humans do it so well that it's almost, it makes it harder to put down into code.
You could say that about, like, image processing or audio processing. And I feel like when you look at the progress in terms of, like, facial recognition or, like, understanding voice, it's, like, really spectacular, right? Like, we see it, like, in our lives all the time, for better or worse, right? But I feel like we don't see like robots running around like we might have expected. And like the feats that robots do that I'm kind of wired to be impressed by are actually, like, incredibly unimpressive to like my mother, right? Whereas, like, I think in every other field, the stuff that ML's doing is sort of amazing, like, compared to a human. But I feel like in robotics, we, like, look at what a Roomba does, and it's like, it kind of blows our mind. But, my cat can do much more impressive stuff, right? Less helpful, kind of creating a mess instead of undoing it. But still, like, why is, like, robotics so particularly hard?
So the similarity problem, once you get past something concrete, like this face belongs to this person in different situations, but here's, like, I'm in a city I've never been before. If I had to guess which way the hospital is, how would I do that? And so, like, we have a lot of subtle things that we do to, like, get oriented in novel situations. That's one aspect. Another is that machine learning, the way it's set up right now, it requires just a whole lot of data. So to learn basic things, categorizing images, which is like something that we train animals to do on a regular basis, not even very brilliant animals. That requires huge amounts of well-labeled data. And if you get some poorly labeled data in there, you can mess it all up. to learn things, to do a thing where you've like maybe never done it before and you have to make a reasonable guess your first time.
Mhm.
You know, there are some people making efforts in that direction, but it's still very early days.
What do you think about the approach of kind of simulating data? Does that seem promising to you?
Yes. In fact, another thing that's really hard about doing robots is it's hard to keep your robot up and going. So if you ever worked in a robotics lab, if you get like 3 solid runs, it's like, great, you write that up. That's your thesis. You're done like before the next spring breaks. So a simulation is really useful for that because you can run a robot for thousands of years in simulation time and generate that volume of training data. It's not without its pitfalls, though. I've worked with simulations, and if you talk to anyone who has, they'll have a story about how there's some quirk in the simulated physics or the simulated world, and your reinforcement learning agent learned to take advantage of it. So like in mine, there was this 7 degree of freedom robot arm, and it learned to reach down into the table because I made it too soft and use the table as a guide and then come up underneath the thing it was supposed to pick up. So,
Oh my God.
there was a paper that came out not too long ago about open AI using a shadow robot hand with a whole lot of robot simulation to do some of the steps to solve a Rubik's Cube. And a good part of what they did was getting the simulation right. And in fact, if you read closely, they actually went back and modified their experiment and their physical hardware in order to make it simulatable. Like it does not come easy, but potentially it's a really useful thing.
What is the toughest part about going from a model on your laptop to something in production?
So when I'm working with data on my laptop, I run it. It all fits in RAM. Get an answer, spits it out. Whatever makes an image, saves it to a file.
Yeah.
That's all good. Get an acceptable error rate. I'm good to go.
Mhm.
Taking it into production, that trained model then becomes like the easiest part of the whole thing. Depending on what you're using it for, let's imagine you're using it as part of an app or part of a service where somebody somewhere on their phone or on their laptop has to do something that needs the result of this. Let's say it's a weather predictor or a coronavirus risk predictor or something like that. All of the pieces to get that request, to make sure that it's not part of some, denial of service attack, to put make sure that the request is well formed and it's not going to like gum up your model, to get the answer out, to make sure that it gets delivered. All of those pieces are break them down individually and they're fairly simple. You put them on a piece of paper and it looks like a bunch of blocks connected by arrows. And it's like, oh, okay, here's what all the things do. That's great. But I don't do this myself, but I sit next to people at work who spend their days making sure that all of these blocks run smoothly and all of these arrows are working the way they're supposed to. And it is a full-time preoccupation or a full-time demand on your attention to care for and feed these. They're all running on computers that are in data centers somewhere. They're all running on software that's being regularly updated. Anyone who uses Amazon Web Services is probably familiar with new services and new capabilities coming all the time. Occasionally there are breaking changes, so what worked yesterday doesn't work today. And it is a lot harder than it sounds when someone tweets out, oh, cool, I spun up a cluster and now this thing's running 1,000 times faster. And it's like, that's super cool, but that hides a lot of effort that goes underneath. And it also hides a lot of the long-term investment required to keep that up and going.
I guess though, I totally agree, but the things that you've described feel like the difference between sort of any kind of demo on your laptop and any kind of like production thing. But I do feel like there's at least kind of like a trope or a meme or something about how like machine learning is like particularly hard to do this with. Do you think that there's something special about machine learning that makes it extra hard to put the stuff around it and make it stable? Or do you think it's just, people just get too excited about demos in general?
Yes. So machine learning specific issues are it's almost impossible to consider all the possible inputs you'll get. For instance, if you want to take an image as an input and say, put a filter on it or do some kind of identification on it. And so it's very possible that, basically your users are now adversarial. And some people out there are going to either intentionally or on accident come up with things that will break what you're doing. And so being able to identify that, I mean, it may not take the service down, but it might produce a result that's undesirable or offensive or at least embarrassing. And so you kind of have to keep an eye on that. The other thing is a lot of times when we train a machine learning model, there's, a training set, validation set, maybe a test set. If you train it, you get good results on that data and you go. That assumes that the world doesn't change, which is a terrible assumption. Because as soon as you deploy that model, whatever phenomenon you were modeling is going to start gradually shifting. So a great example of this is weather. So if you had a really good weather predictor in 1970, it would probably not be worth very much today. And having the ability then to not have a static model or to periodically retrain and redeploy is important if you want to keep that up and going. Those are the two big ways that I've seen machine learning models in particular fail.
Okay, you wrote yourself a really, really softball question, but I'm kind of dying to know how you're gonna answer it. So here you go, Brandon. What's so great about robots?
So I've alluded to this already, but there's more. So for me personally, there is passion around robots. When I was a kid, I'm 5 years old and I'm watching The Empire Strikes Back in the theater. And Luke, at the very end, he gets his hand cut off, of course, and he ends up with this prosthetic hand, and there's these mechanical actuators in place of tendons. And I just thought that was the coolest thing I'd ever seen. So that right there kind of set my career path. And so, I'm in graduate school now, mechanical engineering, and working with prostheses and stroke rehabilitation. And I have like circuit boards out, and I'm on the phone with my dad, who's an analog electrical engineer. It's like, hey, I need to build a preamplifier for this signal because the sensor is not strong enough. And I have to package up and shrink wrap it and tape it to this, motorized prosthesis that we're putting together. And then I have to read it in through the serial port and write some C code to pull the values off of it and read it in. And it's just it's down in the electrons, it's the interface between the physical and the software world, and maddening and frustrating. And so many times it doesn't work. And then, after weeks, it does. And I just stand back and I look at the thing and I think, whoa, this is there's no boundary between the real world and the imaginary world and the computers. It's all real. There's physical and there's digital, but there's a blurry line in between. And robots span this. And so with robots, you embrace all of the chaos of this physical world. And you really have to put your money where your mouth is with regards to control and learning. And that your sensors are going to fail, and that your actuators are going to change performance over time. You have to be able to handle all of this stuff. And when you're done, if you do it right, you have a little thing that, if you suspend disbelief, it looks like it might be alive in some small, cool way. And that's pretty cool. That gets my motor going.
Okay, so I got to ask you. So one thing I think about is it feels like we don't actually engage with many robots in our lives today, but I don't think it's so much the cost of the materials, right? I mean, iRobot maybe has one good example of a robot we do use regularly, but it seems like there's a lot more things where you could build them, but it would be hard to kind of make them smart enough to be useful. And software is so amazing, right? Because once you make it once, you can copy it and put it in everything. I sometimes wonder if a day will come that there will be robots just all over the place doing useful things for us. Do you imagine that will happen, or are there like breakthroughs that are kind of unforeseeable? What do you think about that?
I very much do. And this, the reasoning, the chain of reasoning you just followed is exactly what I did when I was, in my graduate program. And I'm looking around and I'm thinking like, yeah, hardware capabilities are pretty cool. There were some robots at the time out at Berkeley that had crazy number of degrees of freedom, big as a person, could do all kinds of things. But the gap between what could I do if I was controlling it with a joystick and what can it do with its own brain was so big. And a joystick's not even a very good interface. What could I do if it was tied right into my brain? It's like
Yeah.
huge. And I realized that I wanted, if you go into robotics, typically you focus on hardware or software. So it's like, well, software seems like the bottleneck here. So that's what I'm going to focus on.
I see.
For now, a lot of the emphasis on machine learning methods is driven by performance on benchmarks. That's good if you have to publish papers. You need some basis for saying this method is as good as or better or close to some previous method. And the benchmarks are good for that. But it's gotten to the point, in my opinion, where the tail's kind of wagging the dog, and we only pursue the problems that we have good benchmarks for. So image classification, in all the world of machine learning stuff, image classification is a tiny, tiny little piece of problem you could solve, but you wouldn't know that based on popular press and based on a random sampling of papers at NeurIPS, for instance.
Sure.
So that is starting to change the last couple of years. You see a little bit more kind of like people going rogue with architectures or with the problems that they're willing to handle. And I think more people are losing a little bit of patience with like, okay, image classification, like facial recognition is just another flavor of image classification. We can do all this pretty well, but we are really like bending our universe around this one point. Why not branch out a little bit? And as we're willing then to cover a little bit more of the space of the problems you have to solve, we'll get robots who, like the Roomba, you might not watch it and think like, man, that's like vacuuming more efficiently than I would. But you watch it and you think like, okay, it's getting to all the corners, all the edges, covering everything in its own time. Like, great, I can go off and have a coffee and be confident that it's going to do its job. I think we're going to get more and more of that.
Cool. That's so cool. And I got to say, I think the biggest pleasure of doing an ML tools company like we're doing is getting to talk to guys like you who are actually kind of taking these applications into, or taking the technology of machine learning into these applications where you like really see them. And it's so cool to just, kind of see machine learning going everywhere. So I share your excitement. We should bottle up that. I feel like your answer to why a robot's cool. It's like we should like make that like a video on YouTube, and everyone will want to go into robotics. It's like so well articulated and enthusiastic.
Thanks. Oh man, I would be all behind that.
I remember I watched Return of the Jedi in the theaters. I think I might be like 2 or 3 years younger than you. It left me like catatonic and like nightmares for years. So it's like a pretty different experience.
Yeah, no. Positive. Apparently Han getting frozen in carbonite was not a traumatic thing for me at the time.
So cool. So what do you think is one underrated aspect of machine learning that you think people should pay more attention to?
The next neighbor that I'm really excited about. So we have like, image classification, also some really cool things with word prediction are happening. Ripe for the plucking is unsupervised methods. Being able to automatically do clustering, automatically learn the similarities between things that are, may have many variables, might be really complex, but to be able to say like, I've never seen this situation before, but it's kind of like this one I saw in the past, and to be able to make use of that, what we've seen before. I think that there's a lot of work that could be done there for a modest amount of effort, and it suffers mostly from the fact that there's no one right answer, and so it doesn't lend itself to benchmarks. But, if anyone hearing this wants to say, screw benchmarks, I'm going to go work with unsupervised learning, like I expect it would be a really fruitful way to spend your time.
Ooh, interesting. I want to debate you, but we're running out of time. Intriguing. All right. So next question is, what is the biggest challenge of machine learning in the real world?
If I had to pick one that is the biggest in terms of impact, it is misapplication. It is easy to, treat it like a hammer and beat on anything with it without regard to whether the hammer is the right tool for that. Mm-hmm. And so we see places where, models are trained on a grab bag of data about people that can transfer biases and transfer historical injustices, because those are the processes that generated this data, and the new model will just blithely perpetuate that. And there are few people who are kind of intellectually in a position to see how that works. Some of them are wonderfully vocal, but it's still not all of them. And I think that the biggest downside, the biggest difficulty, is that those who don't know or don't want to know about that will continue to use and perpetuate these to end up hurting people. And
do you have a particular example that specific bothers you, or that you'd want to call out?
So facial recognition in law enforcement is one that comes to mind right away. It is demonstrably inaccurate, and especially for non-white minorities, the accuracy is even worse than average. And so it's just a way to cause many more problems than it solves. On the surface, especially when sold the right way, it appears to be a useful tool, and you can make lots of great claims about it, but that washes over the harms that it does. And that's not even touching facial recognition used for like overtly, discriminatory purposes, which is, completely unethical in my opinion.
All right. Well, let's close with one final question. Is where can people find you if they want to keep this conversation going? What's the best way for them to reach you?
Yeah. So I'm online, fairly active on Twitter. Handle is _BROHRER _. Also on LinkedIn, regular posts, Brandon Rohrer. And a lot of my choicest stuff, my labor of love, goes to the end-to-end machine learning school, some course materials I put online. And that's at e2eml.school. So e2eml.school.
Very cool. We can put all these in the notes too, so people can find them easily.
Fantastic.
That was awesome, man. That was so fun. Thank you so much.
Thanks, Lucas. I really enjoyed the conversation. I appreciate you and Lavanya setting it up.
All right. That was such a great conversation. Thank you, Brandon and Lucas. I'm going to add a link to Brandon's Twitter account and also to his course in the show notes below. I highly recommend that you guys check it out. If you'd like to continue the conversation, we do have a very active Slack community with over 1,000 machine learning engineers, and I'd love to see you guys there. I'll add a link to the Slack community in the show notes below. Before we end for the day, I'd love to talk to you guys about something that I'm super excited about. So at Weights and Biases, we love traditional machine learning as much as we love deep learning. So we built a scikit-learn integration that lets you track your model performance, compare different models, and be able to pick the best model. We also help you do hyperparameter sweeps on your scikit-learn models that let you find the best iteration of your scikit model. With one line of code, you're able to create really cool plots like the ROC curves, precision recall plots, learning curves, confusion matrices, calibration curves, and a lot of really interesting classification, regression, and clustering plots. I'll add a link to the show notes below so you can get started right away. I would love to have you guys give it a try and tell us what you think. We're always trying to make our product better, and I would love to hear feedback from you guys. That's all for today. We'll see you next time with another great episode. Bye.